Hello everyone. So I hope I'm audible now. So let me start the screen recording here. So let me hide this first. So I'm Dushar Jaiswal and this is our course CML102 and this is the second assignment that we have to do. So in the following assignment we have to do the following task. Let me just open what we have to do here. So it is the assignment 2 in our course CML102. So basically, it's all based on the crystal structures, and we have studied about the X-ray diffraction patterns, powder X-ray diffraction patterns, and different things. So we have basically used our knowledge and to we will provided with structures and with the intensity patterns, and we have to use our knowledge to create the structure, and then after once we create the structure, then we have to compare it with the real crystal structure. Like one can obtain the crystal structure from the powder X-ray diffraction pattern. Here we are just using the intensity thing to compare, and we can see how close we can get to the real structure. So what we have to do in this assignment is we have to solve and then refine the crystal structure using a tool named as OLX2 software. Okay, and so we have given with the data is named as SCXRD data. It is provided by suggested in our tips. So I will let you show what are those data. Then we have to make a crystal packing diagram using the software Vesta. In the previous assignment, we learned how to use software Vesta, so we can just easily go through that. Then we have to stimulate the powder XRD pattern of the structure that we have made. So we have made the XRD PXRD that powder XRD fraction pattern of the solid structure that we have made, and we can easily compare it with the actual XRD data that is being provided, so we can just able to know how better our solution is. And then we have to just basically make a report of all these tasks and present in a short video. That's what I'm doing here. So let's begin. So I have made a little bit of the assignment here, so one can just go through it. So I will just upload this doc file there too. So let me just go through this doc file. So before beginning, like we can discuss some important concepts. So few important concepts are that when used here is the refinement, and the R factor is one of the important concept that is used here. For the exit diffraction, as we all know, it's also is an important thing to know. So in the process of the refinement, it is like basically the process of making the structural model more closely match experimental data is known as refinement in crystallography. Means that we are trying to reach over the more, like refining the structure more and more and more, so that we can get to the like the experimental result that we have obtained, we can get closer to that. So our structure will be more better. It's like basically the structure model correctness and dependability is enhanced by this statistical procedure. Then we use XRD like Vesta software to analyze a powder X-ray diffraction pattern. I will let you know how we have done that thing. And then moving ahead with the R factor. So R factor is a very important concept here. That this is basically a numerical measure that assesses how well the suggested structure model, that the model that we have been suggesting, and the real crystal structure agrees. So like basically when it's the R factor is less than 5%, like R value is around 0.05, something like that, it's a very good agreement with the calculated and the observed structure. So it is a really important factor, so we can just can understand our salt structure is right or not, like it is agreeing with the observed structure or not. So let's get to the basics. So basics are like we have to just install the OLX software here. Once we install, we have to do some following processes like inserting the select program in the OLX folder so that it can be run by the select team. Then we have to there is a two file. So we have to access the INS file. It's basically information file. It is coded with the information of the intensity pattern that we can use. Once we just open it, like we can just able to show the electricity electron density points. So it will show location of the electron density points, and then we have to assign the atoms regarding that. That we will name the electron density as carbon, oxygen, sulfur, nitrogen. It depends on the question. So and then we have to improve the structure. We can use the R factor thing here. We will try to minimize R factor as much as possible. Then after once the R factor is reduced and we have made the all bonds, we just make a similar structure. Then at the end we can additional modification can be done there. We can add a hydrogen so that it will be a more like more better towards the real structure. After doing all this, once we are done with the structure, then we can create a CI file by using this ACTA capability. It is an option given in the tool. Then after once the CI file is created, we can use Vista to visualize it. Once we launch, then we have to launch the Vista. We can observe the structure of the solution that we have provided. And you can also get a forward diffraction pattern using the Vista. So just let me begin. Here's OLX2 software. So let me just show you something. Assignment to Tushar. So the task one is regarding the data one is hydrochlorothiazide. So we have to basically see structure. So here is basically the structure of the hydrochlorothiazide. You can see we have different labels. So carbon here is a carbon here is forming a planar ring. You can see this carbon here is forming a planar ring. Then it is attached here by the nitrogen here. One nitrogen is here and one sulfur is here and other sulfur is there. So it's like that we have to identify, like once we identify the carbon atom, so because it was a planar one, but then we did this little bit difficult to understand where will be the sulfur and the nitrogen will be there. So we have make different assumptions like one of the thing is that the bigger the size of the electron density, like here you can see that it is an electron density atom. So more its size, we can just know that it is like a belong to a heavier atom. So it's more easy to express like this. And then after once we make this structure, we add hydrogen at the ends, like this is the where we had the hydrogens at the end of the molecule. This is R factor. One can see it's 3.76% here. It's very like it's less than 5%. And it's good. Like we have done a very good. And after doing the refinement, like we can just go and work and then refine it again. And you can see the structure again and again. And it's like one we have defined it very carefully, so one can get the structure. So and to add one more thing, we have use the structure of the hydrochlorothiazide for the reference. Here you can see the planar ring of the carbon, it's like benzene, and then it is attached by the nitrogen and the sulfur. Sulfur with a double bond of oxygen. So you can just go and check over it. Like once you open this, you can see here it's carbon here, then it's nitrogen here, and the nitrogen are here, and then okay, the nitrogen is here, and then sulfur is here, and sulfur is double bonded with the oxygen atoms here. You can see the structure here. Let's move ahead. No, before moving ahead, let's go to the. Okay, let's move ahead only. So, the second part will be regarding the data 2 is for the raluzole along with the malonic acid that we with the compound formula of C11H9 and 2O5F3 sulfur. So here for this we have the reference images. I will just go through it. Let me just show you the data. So it is here. It is rhizomol and the malonic acid. You can see the planar structure of the carbon rings here. Then the carbon rings then attach here. You can see the sulfur and the nitrogen are here. It's basically you can just go here and it will be like this only. This is a ring formed by the carbon atoms, and then it's sulfur and the nitrogen. And one thing is also here. You can note that identifying nitrogen and sulfur is a little bit difficult, but one can use a bond length concept here. So it's like the bond length is given here, and it was 1.7 and it is 1.3 for it. So double bond length is usually shorter. So like nitrogen is making double bond with one carbon. So it should be of small bond length. That concept we use to identify the between the nitrogen and the sulfur. And similarly, the malonic acid structure is also provided to us so that we use that thing. Let me just go here. Let me. Oh, I just opened this thing. Okay. This is the malonic acid with a molecular formula of C11H9 and 2O5F3S, and it's a 3.89 R factor. This is here. And you can also show the hydrogen bonding form here. So it's like it's it's basically like one of the hydrogen, one of the oxygen atom is making hydrogen bonding with the hydrogen atom here. You can show, you can just observe it here. Yeah, this is a one hydrogen bonding observe. We will see out more about hydrogen bonding in the Vesta software. Like when we move ahead, similarly when we move ahead to the third part is ribosol is along with the orthophosphoric acid salt. So first thing the structure is for ribosol will be same. For the orthophosphoric acid here, I have provided structure of acid. For the salt, OH will be removed from here. So it will be like PO double bonded OH and OH. So this OH will be removed from here. And we can just go to the here and we can see the its file. It's basically C8 H8 N2O5 F3PS and we got R factor of 3.57 which is quite good here. We can refine it again if you want to see and after some refinement 3.56 R factor. You can see here the carbon atoms are in a ring. And there here you can see orthophosphoric acid here, and this orthophosphoric acid oxygen is hydrogen bonded with the hydrogen which is attached with this ribosome of nitrogen. Here you can see nitrogen is attached with hydrogen, and then there is a hydrogen bonding here. That's a good thing. Yeah, these are all the things that we can see here. So coming like the first part of our assignment. Then we move to task 2. Here in the task 2, we simulate the following structure in the Vesta software. So let me just open my Vesta software here. Here is my Vesta software. So I have captured it from the three axes like A, B, and the C. Here the first is for the height. So the first is oh, let me just capture the name again. First is for the hydrochlorothiazide, and you can observe its structure here. So let's go here. So it is like a structure you can see from the different axes. Here the carbon rings are here, and then attached by different different nitrogens and atoms of different things. One can see the red are represent oxygen here. These are the nitrogen here that are joined here. So this is the following structure of that we have made of the hydrothiazide. You can observe it through different aspects. See different aspects. You can just have this slope. Hmm. Similarly, we have the other thing. Other part is for the second part is for the xylosol plus malonic acid. Here is you can say xylosol plus malonic acid. So we observe its structure here. You can just go over the Vesta thing and just go for the element. And one of the thing that we want to see here is the hydrogen bonding. You can see the hydrogen bonding here. So basically, oxygen atom is here. Even if you look here pretty closely, but this is the ring of the carbon. Then it is attached by the nitrogen and the sulfur. Like here, you can just go scroll through it, and then you can just you can just see the structure of this. So it was like nitrogen and sulfur rings are there. So over the vista, you can see that it's like carbon atoms, planar rings are there, then nitrogen and sulfurs are there, and you can also see the hydrogen bonding here. You can see the oxygen and the hydrogen are making bonds here. This is like a intermolecular hydrogen bonding that is happening here. Similarly, let you can observe it from the three different axes too. Yeah, A, B, and the C. Here B is more clear. You can just like observe the clearer carbon ring, then hydrogen atoms between the hydrogen bonding with oxygen and the hydrogen here is observed. Similarly, we move to the third part here with like orthophosphoric acid. We can view it from the three different axes also, like A axis, you can observe it, and for the B, you can also see. So this is a molecule here. So you can see that like these are the orthophosphoric acid and which are orthophosphoric in the orthophosphoric acid the oxygens are attached to the hydrogen of the xylosol by the hydrogen bonding here. You can clearly observe it. They are joined by the hydrogen bonding here. This hydrogen bonding if it is not properly shown in the OLX software, we can observe it very clearly in the Vesta thing. And just call this. So these are the two parts that have been done here. And then moving to the last part here. That is the task 3 of your where you have to provide a powder exit diffraction pattern. So let me just simulate how we can draw the powder exit diffraction pattern. So we just to go to utilities and here's the powder exit diffraction pattern. You can just go there and you can observe it. One thing that need to be measured is the angle is in 2 theta degrees and we have talked about it and why it is like this only. So we have mentioned it why it's shown like this. Let me just got it again. So these peaks are there, which are indicating that it's not an amorphous, it's a crystalline form. So we are getting peaks at certain specific angle, and it's like at for certain angle, like here to it about 80-90 degree, is then intensity is very high, up to 100. So this is for the first thing. Similarly, we can go for the other two structures here. You can go for the utilities, then for the diffraction pattern. You can also easily observe it here too. So this is also a crystalline structure. If it is an amorphous, it would be like not continuous enough. It should not be a peak there. Then it should be like a hump. And for similarly for the third part, you can go to the utilities and for the diffraction pattern, you can easily observe it. And one of the thing interesting it is that the peak is observed very early angle here. And that's all here we can know about it. So just let me close this part here. So this is all that we have to do here. Three tasks were provided to us. We have made the digital packing structure using the Vista. We have solved the structure using the OLX software. We have simulated a PXRT XRT pattern here, and we have provided a video. I will upload the video same. Thanks for listening to me. This was a very good assignment. Let me just end this. Thank you so much, sir, for your time.